Good morning, Advanced Chemistry. Today we're going to take notes on 3.2. Understand what is meant by a reaction mechanism and propose a potential reaction mechanism for a multi-step reaction. So here we go. What is this reaction mechanism that I speak of? It is a detailed description of the pathway followed as reactants become products during a chemical change. It is also a series of elementary steps, each requiring the successful collision of only two reactant molecules. So a reaction mechanism tells us a lot about what's going on in a reaction. So you have the overall reaction that takes place in a series of steps, and this is evidenced by laboratory information showing that there are actual steps that take place as opposed to one reaction happening all at once. It's like a series of mini reactions that combine for an overall reaction. Here's an example of a reaction mechanism, and first thing I want you to look at here is the overall reaction here at the bottom. We've got 4 HBr plus O2, so it's a combustion, making 2 waters and 2 diatomic bromines. And I want to just talk about for a second why this is necessary. If you look at the reactants, you have 4 HBr's and an O2. So that is going to require the successful collision of 5 molecules. So you've got the 4 HBr and the 1 O2 molecule that are all going to have to collide with the correct energy and orientation for this reaction to occur. And that is really unlikely to happen. So because you have more than 2 molecules that have to collide successfully, that is a really solid indicator that this reaction is going to take place in a series of steps. So instead of having to have those 4 HBr's and an O2 all collide perfectly, this reaction takes place in a series of 4 elementary steps. So they're called elementary steps. Here you've got 1, 2, 3, and 4. And so these elementary steps, if you'll notice, they each have just 2 molecules that have to collide. Just 2 in each case. And they combine, if you look at the overall reaction, and you were to cross things off that appear on both sides and combine, here you have an HOOBr showing up on 2 sides, and then you have 2 HOBr's, and then you have 2 on the side. And then, as I said, combine, so you have 1, 2, 3, 4 HBr's and O2. You've got your 2 waters right here, and your 2 Br2's right here. So if you combine everything that happens in those 4 elementary steps, you get the overall equation, but each step occurs with only 2 molecules having to collide. Also over here on the side, you'll notice that each step has a description of how slow or fast it occurs. So that helps us to decide what's known as the rate determining step, and that is step number 1. So the rate determining step, or the RDS, is always the slowest of the elementary steps. So I'm just going to write in here, rate determining step, or RDS. And that's always the slowest one of all your elementary steps. Because in this case, it's like this reaction cannot proceed until this step gets done. So the entire reaction is depending on the speed of the first reaction. You've heard it said that a team is only as strong as its weakest link, or something like that. This is the same kind of idea, except for the whole reaction is only as fast as its slowest step. The other thing I want to mention with this particular mechanism, our 4 elementary step mechanism here, is that we have a perfect opportunity to talk about an intermediate and what an intermediate is. An intermediate is something that is both produced during and used up during the elementary steps. So it doesn't show up in the overall equation. Now, your intermediate in this particular mechanism is your HOBR, and there's 2 of them. So you can see here the HOBR is made, and here HOBR is used up. And you have one more that is also an intermediate, and that is your HOOBR. So here it is made, and here it is used up. So an intermediate is something that doesn't appear in the overall reaction. An intermediate is something that is produced and then consumed during later elementary steps. So it's like it was never there. It doesn't show up in the overall equation. It is there, but when all is said and done, it doesn't look like it was there, because even though it was made, in a later step it was used completely. So what you're looking for with an intermediate is something that first appears on the product side, but then later is completely used up on the reactant side. So that's what's known as an intermediate. There is another component that you can identify in a reaction mechanism, and that's a catalyst. And you've been dealing with catalysts a little bit in your lab and talking about catalysts, but catalysts can show up in reaction mechanisms as well. So right off the bat, the first thing I want to do here is look at our 3. We've got a different reaction now. So here we have, looks like the decomposition of acetic acid. And that's our overall equation. We've got a delta H of positive 72.8, so it's an endothermic reaction. And we've got 3 elementary steps. The first being very slow, very fast, the second one being slow, and the third one fast. So our rate determining step is step number 2, because the whole reaction is very much determined by how fast that middle step goes, since it's the slowest. So let's see if first you can find any intermediates. So I'll have you look for any intermediates. Maybe pause and try to identify those first. There are at least 2 intermediates that I see here right off the bat. The first is this this ion, HCOOH2 positive, right there, which is made in step 1 and used up in step 2 completely. And then you have one more, HCO plus, another cation, is made in step 2 and then immediately used up in step 3. So those are your intermediates. But what I want to talk about now is the presence of a catalyst. So catalysts. Catalysts are something that it's sort of like the opposite of an intermediate. They're there at the beginning, and they're there in equal amounts at the end. So it appears as though they were not used up or changed at all. So your catalyst in this case is your H plus ion. So if you'll notice, you have an H plus here at the beginning as a reactant, and it's not consumed anywhere in the reaction, or it doesn't appear to be consumed, because you have exactly the same amount of H plus at the end. So therefore, if you were to be crossing things off in your reaction, you would cross off your intermediates because they show up on both sides, but you would also be crossing off your catalyst because it would also be showing up on both sides, but it would be in reverse. So catalyst is something where it's there in the beginning, but it's also there in equal amounts at the end. So it doesn't appear to take part in the reaction because it's unchanged from start to finish. So if you're going to write a definition for catalyst, it would be something, of course you guys know that it speeds up the reaction just by being there, but it is present at the beginning of a reaction, but is not consumed in the overall reaction. So in other words, it's there to start, but it's not changed or consumed during the course of the reaction. It's still there by the end. And like I said, you guys know that a catalyst, its job is to speed up a reaction, so I want to talk about that too. But hopefully by now you're able to kind of look at a reaction mechanism. I want you to be able to identify the rate determining step, which is the slowest step, any intermediates, and any catalysts. Now let's talk about what a catalyst does. So I've got this H plus here. What is its job? Now it has to do with lowering the activation energy of a reaction. So we talked about activation energy in the previous notes, but every reaction has a transition state, which we identified as the highest energy spot on the pathway between reactants and products. And so if I'm going to have energy on my y-axis and reaction progress on the x-axis, and we'll use the last mechanism that we just looked at for an example. That was an endothermic reaction. So if we have reactants down here and products up here, because it's endothermic, then we're going to go up. Delta H is going to be the distance from our reactants to products. So delta H is the distance in energy between reactants and products. Now we've got a transition state here, and the activation energy is the distance from the reactants to that transition state. Now what a catalyst does, the presence of a catalyst's job is to simply lower the activation energy. So what a catalyst does is it takes that transition state and it makes that transition state lower in energy. So look at what that changes and what that doesn't change. The energy of the reactants is the same, and the energy of the products is the same. So delta H is the same as it is without a catalyst. So the overall delta H, the overall change in energy is the same, as is the amount of energy of the reactants and the amount of energy in the products. What it does change is the amount of energy of the transition state. So that is different, and it also shifts the activation energy, so it is less than it was before. So the activation energy is less and the transition state energy is less. Doesn't change delta H, doesn't change the value of the reactants energy or the products, but does shift the activation energy down. And all that means is that now in collision theory, the amount of energy it takes to get over that hump of the transition area to the products is less than it was before. Therefore, the reaction should be able to proceed faster because it doesn't need as much energy to achieve that transition state. It can simply use that energy in its collision to go straight on to the products, and it can do so faster. So that's the job of the catalyst. That's it for me. I hope you guys have a really, really good rest of your Monday, and I look forward to seeing you tomorrow. Bye.